What are numbers? How do they work? Why did we conceive of them in the first place? Why are they useful? That is the number one question that so many people ask about math, is why is this useful? So I'm going to start at the very beginning. My name is Professor Cunningham, I've got a snazzy new jacket, and this is MathQuest. As a student of math, you may feel like numbers and the math associated with them were invented just to confuse and torment you. But in reality, their purpose is exactly the opposite. One of the basic fundamentals of math that I have such a hard time getting across to students is that each new idea in math is intended to make your life easier, not harder. I know that can be hard to believe given how abstract and complex the ideas can seem, but what you don't really see is the alternative. What if we didn't have math? What if we didn't have numbers? How would our lives change if we didn't have these concepts at all? Other than you not having to deal with math classes and homework and tests. The best explanation I've been able to find comes from one of the best sources for very early mathematical knowledge, Sesame Street. Let's take a look.
The phone.
I'll get it! I got it! Oh, man! Oh, ow.
Hold on. It's for you, Humphrey. Here you go.
Thank you. Yellow, furry arms, how may I help you?
We're hungry.
Well, what would you like?
A fish.
Fish?
A fish.
Fish?
Fish.
Fish?
How about you guys?
Fish.
Fish, fish. You got it?
Well, let me repeat that. Fish, 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 fish.
You got it!
All righty, be right up with that order, Mr. Penguin, sir.
Yum.
Ingrid, go tell the kitchen, fish, 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 fish.
Fish, 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 fish.
No. Fish, 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 fish.
Not that easy in order, but I'll get it.
Ernie goes on to teach the two how to count the fish, but we're going to explore the idea of a world before numbers. And we're going to do so by exploring a hypothetical situation. Before I start, I want to make it clear that this isn't intended to represent how numbers and counting were actually created in history. The history of numbers is complex and fascinating, and the two subjects of math and history are much more closely tied together than most people realize. However, in this video, we're speaking purely hypothetically. With that out of the way, let's get started. So let's imagine that you live in a world before numbers, a world where numbers don't exist. Further, let's assume that you make your living by herding sheep. Here's your shepherd's crook. Now, it doesn't have to be sheep. You could herd cows or llamas or ostriches or any other grazing animal. I would avoid emus, though. I don't know about you, but I wouldn't want to try to herd an animal that was able to defeat Australia in a military conflict. That's true, by the way. Sort of. Anyway, you've got some sheep and you keep them for their milk and their meat and their wool. Or perhaps only for the wool, which you gather using only the gentlest and most humane shearing techniques. By night, you want to keep your sheep in a pen. That makes sense. It has a couple of benefits. First off, every morning you'll know where all of your sheep are. They'll all be gathered in one spot. Also, it keeps them from wandering off and being eaten by wolves or bears or cougars. Every day you let the sheep out of the pen and you walk around with them and keep an eye on them while they eat the grass. Every evening you bring them back to the pen. Now, when you get back from grazing during the day, you want to make sure that all of your sheep are still there, right? I mean, no matter how careful you are, now and again, some of them might just wander off when you're not looking. That represents a risk to you. Fewer sheep means less wool to trade. We may not have a concept of numbers yet, but that idea is still pretty clear. So, how do you deal with this? Well, if your flock is small enough, you might be able to just recognize each sheep by sight. You might even go about giving them names so that you can keep them better in order. But what if your flock is bigger? No, bigger. Bigger. Sooner or later, no matter how good your memory is, you're not going to be able to keep them all straight in your head. You need to be able to come up with a better way of quickly determining whether or not any of your sheep are missing. I'm going to give you a few moments to think on this, and I encourage you to pause the video and really think about how you would solve this problem. Now, there are several possibilities, but I'm just going to give you one. As you're looking at the ground pondering this problem, you suddenly realize there's rocks all over the ground. This gives you an idea. When you let the first sheep out of the pen for the day, you pick up a rock and you put it in your pocket. Every time another sheep exits, you pick up another rock. Once all the sheep are out, you take them and your pocket full of rocks and you go. When you come back that evening, every time a sheep re-enters the pen, you take a rock out of your pocket and you put it back on the ground. Sheep comes in, drop a rock. Sheep comes in, drop a rock. The idea is that when you're done, you should be dropping the last rock as the last sheep comes in. If the last sheep comes in and you still have rocks in your pocket, then you know that some of them went missing and you're going to have to go find them. Now, I know this idea seems simple, but it has some really major consequences. By creating this tool for tracking sheep, you have created, or discovered, we'll talk about that next video, two very, very fundamental and important ideas in mathematics. The first is that one thing can be used to represent another thing. In this case, a rock is representing a sheep. A rock and a sheep don't look anything alike. They have nothing in common. Yet somehow, you understand that for the purposes of your problem, the two are somehow equivalent in some way. More amazing even than that, you begin to realize that this pile of rocks and this flock of sheep have something in common where before they had no similarities whatsoever. You can pair them up, rocks and sheep, without having any of either left over. This means that there is something, some quality that is somehow the same between these two groups of very, very different things. That quality is called cardinality, and it exists whether or not you have any numbers to express it. In fact, later, when we start talking about the same number of sheep and rocks, what we mean is that you can pair the two up one to one without having any left over. Stranger still, this quality of cardinality doesn't seem to have any connection to the objects themselves. The objects themselves are almost irrelevant. Let's go to Sesame Street again for an explanation.
Does it work on other stuff? Say cinnamon rolls?
Yep.
Cream pies?
Sure.
Spark plugs?
Absolutely.
Wow!
Wow.
Now, this idea works. Sort of. It still has the problem of not being able to deal with very large flocks of sheep, which is a problem that we're going to see a lot for the rest of this video. After all, if you have a very large flock of sheep, that's a lot of rocks to be hauling around. Perhaps instead, you grab a slab of wood or bark. You use a burned stick or some other writing utensil to make a mark on it for every sheep. At the end of the day, you can compare the marks to the sheep and see if you're missing any. This solves the problem of weight, but it still doesn't solve the problem of dealing with very large flocks of sheep. You can group marks together to make little subgroups, but you're still making an individual mark for every single sheep. And again, if you have a lot of them, that's a lot of marks. It's at this point we finally start talking about numbers. The ability to have a name and a symbol to represent certain groups of sheep or rocks or spark plugs or cinnamon rolls is very powerful and very convenient. It keeps us from having to directly compare two groups of objects. So we're going to create a set of symbols used to denote the number of objects in a group. But what are we going to call these number symbols? We need a name. Mathematicians love naming things. Well, it's a number symbol. We could call it a numberal? Numberal? No, that's awful. How about numeral? Now, we can't have separate numerals for every single cardinality out there. You'd have to memorize way too many. It would be a nightmare. Instead, we're going to set up a pattern so that we have a certain set of numerals. How about 10? 10 distinct symbols seems like a convenient number. It's the number of fingers we have, so it works out. And then when we run out, we're just going to scoot to the right and start over. This is certainly a better way of counting our sheep, but it still breaks down if your flock gets big enough. We can add even more symbols to denote larger and larger groups, but even then the system is going to break down eventually. If you want to see how silly this particular numeral system can get, all you have to do is look at the credits of some old movies. Quick, if this were a number of sheep, how many would you have? Again, I really want to impress upon you that this system of numbers that we're coming up with should be as simple and convenient as possible. You should be able to look at a numeral and know exactly how many it is right away. As you can see, this system gets complicated fast, so we're going to abandon it and start from scratch. We're still going to use 10 as our base, but we're going to use brand new symbols. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, we could put a symbol down for 10, but I think we've already seen that that particular system breaks down pretty quickly. So instead of a symbol for 10, you decide to create a symbol for nothing and call it 0. When you present this idea to others, there's a massive amount of resistance to it. Why do we need a number for nothing? What a useless idea. I hate this number because it's making things more complicated for no reason. But you, being the blossoming mathematician that you are, know just how important of a role that 0 has to play in your new system. So let's say you have 12 rocks. Man, it's nice to have names for numbers. It just makes everything so much easier. To write that number, you split it up into a group of 10 with 2 left over. 1, 2, 12. Easy. But what if you had 20 rocks? Now you've got 2 groups of 10 with none left over. How do you denote that? You can't just put 2, because then people won't know whether you're talking about 2 or 20. So you put a 0 in that spot to show that you've got 2 piles of 10 with none left over. So this system solves the problem of convenience, but does it solve our other problem? Can we use it to represent very, very large numbers of sheep? Or rocks, or spark plugs, or whatever? I think we have. When you get up to 99 and run out of numerals again, just make another space to the left representing 10 groups of 10. That could be a little bit confusing, so we'll call it 100 instead. The best part about this system is that it scales up so nicely. 10 hundreds is 1,000, 10 thousands is 10,000 for some reason, and on and on. The numbers that we can represent with this system can be almost unfathomably large. And there you have it. Starting with nothing but a flock of sheep and a pile of rocks, we managed to work our way up to the decimal system that many of us use today. We answered the question of what numbers are, why they exist, and why they're useful. You have to admit, having numbers and counting is a whole lot easier than the alternative. Let's go to Sesame Street one more time for some final thoughts.
See there? See what I tell you? Now you know how many fish to send up. 6 fish.
Holy mackerel! This counting thing can really save a person a lot of trouble.
Yeah.
Now, as I said in the beginning of this video, this is not intended to be a historically accurate account of how numbers came to be. And it's not the only way of doing things. After all, different cultures, both today and throughout history, have used different symbols, words, and even bases in their number systems. The Sumerians and Babylonians used a kind of base 60 system. This is why, even today, there are 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a circle. Now, many of you may have noticed that while we were coming up with this system, we accidentally brushed up against the ideas of addition, multiplication, and at the very end there, exponents. All of these concepts, as well as the many, many more to follow, are natural consequences of creating a number system the way we created it. They can be used to further manipulate the numbers and make them do what we need them to do. And thus, math is born. But did we invent it? Or did we discover it? Is math some sort of universal truth, or is it just something that we humans made up to try to make sense out of a nonsensical universe? These are very big questions, and they don't have easy answers, but I'll give it my best shot in the next video. If anything in this video confused you, that's okay. Ask in the comments, or just stick with me. This was just intended to be an introduction. Every concept that I covered here, I will be covering again in greater detail later on in the series. For now, if you enjoyed this video or found it useful, please like and subscribe. And if you can, please consider supporting me on Patreon or Ko-fi. Some of my Patreon reward tiers include private tutoring via video chat, access to outtakes and other videos, or shoutouts in my videos or their descriptions. Now, I think I've taken the bad math pun joke about as far as it can go, so let me end by just saying thank you for watching and I believe in you. Stick with me and you'll be a mathematician before you know it. See you next time.